Okay, and I'll start recording here too. So yeah, high resolution TM. We learned all about it yesterday, and we learned about it in Chris's talks as well. And today we're going to be doing the practical. So if we go to the end of the slides from yesterday, we had the plan for today. So here we have. So the sample I've got in the microscope today is a carbon film, a thin carbon film, roughly 5 nanometers thick, with gold nanoparticles that were sputtered using an SEM sputter coder for about 5 seconds. And this kind of sample makes a good calibration sample. We know it's pure gold that was sputtered by the SEM target. And we can use it for calibrating things like the diffraction, camera lengths, but also the high resolution images. So it's a good sample to try and make and just have in your sample box, so you can do a quick calibration if needed. So that's what we're looking at today. So we're going to first start by aligning the microscope, and we're going to skip some of the basic alignments, such as the condenser lens aperture and stigmatism, because we already know how to do them, and focus on the ones that are important for high resolution TM. So I'm going to switch over to the microscope computer. So for those unfamiliar with the F200, sorry, the microscope we're using today is the F200. This is the microscope you can see behind me. This microscope has been at UNSW for 7 years now, and it's still working like the day it was installed. It's got a cold field emission gun, which is great for high resolution TM. Gives us a coherent source, which in turn means that when we look at the phase, our electron image goes out to a higher spectral frequency, which is better resolution. So, so this microscope on the view you can see now, this is the view you see when you're operating the microscope. We have a little schematic on the left-hand side, which shows which apertures are in. So you can see at the moment I only have the condenser lens aperture in. I've got a fairly large condenser lens aperture in. So typically when we start the microscope session, we'll be using spot size 1 and angle 5, and that's something we're going to change in a bit. So all that information is displayed on the computer screen. We have the magnification here, and we have the defocus value here. So I hope you can read those. If not, I'll say what they are. Now, we also have here a camera which can look down at the screen, which is great for remote operation and for demonstration such as today. So this screen here with the circles, I'll get rid of the circles so we can see better. I'm gonna. This is just the view of the phosphor screen. Okay, and so now you can see the sample. I'll make that a little bit brighter. Yeah. So this is the sample. So like I said, it's a thin carbon film. So these circles are areas of thin carbon film, and on top of that is deposited the gold nanoparticles. So aligning for high resolution TM, like I said, we've already done the condenser lens aperture. So we can shift the beam to the center, which is here, and check the condenser lens aperture is nice and standard. Maybe needs a slight touch up, like so. Okay. So after doing the condensed lens aperture and stigmatism, the main thing to make sure is that we're focused at standard focus. So with the focus knob, so you can hopefully see my hand in the bottom of your screen, this is the focus knob. If we change the focus value by too much, we can start to see that other effects start to occur. So it's not only changing the focus, but it's changing the alignment slightly of the microscope. So if I go too much, can you see that the size of the features is changing, which means that there's some interplay between the objective lens focus value and the magnification. So for that reason, we want to always be at standard focus. So on the geo microscopes, this is called standard focus. On a Thermo Fisher or FEI, or even Philips microscope, this is called eucentric focus. But this, if we double press, will reset the objective lens current to the standard value. So that's the value set by the engineers during installation, and it's the value that all the alignments are performed at, and it's the value that all the calibrations are measured at. So things like magnification calibration and focus calibration. So from this point, we don't want to use the focus knob for any coarse focusing. If we were to move to a new area of the sample and find that it was out of focus, we would then use the Z control, which on the F200 is here, to either move the sample physically up or down inside the microscope. And so this is bringing the sample to that eucentric plane. And the easiest, or the way I find easiest, to do this focus is to look at the image contrast and to see where the image contrast disappears. And that is, if I get it there, is around what we call minimum contrast. So that minimum contrast is where all of the electrons leaving a point in the image, in the sample, make their way to the same point in the image. And so the change in intensity is minimized, and that's what we call minimum contrast. There are other methods to focus the sample. You'll include an image wobble function, which if I press it and go out of focus, you should maybe, if I have 2 seconds, I will change the strength of the wobbler to make it easier to see. No. Okay. So you should see that the image is now shifting left and right and slightly up and down. So what this is doing is introducing some image shift, and when the sample is in the eccentric plane, the effect of the image shift, like so, is reduced. I think maybe there, and that image shift reduces, and you can use that to find the same minimum contrast position that I found manually just looking at the contrast. So there are multiple ways of finding, I'm going to turn the image wobbler off, but there are multiple ways of finding that eucentric position, and it's slightly sample dependent, but also what you find most comfortable. So, like I said, I find the image contrast most comfortable to do. So now we've set the sample to the right height, and we've set the microscope to the standard focus condition. So the next step is to do the HT wobble. Now the most proper way to do the HT wobble is to first make sure that tilt shift purity is corrected. The way we do that, there are multiple ways to do that, but we use the tilt wobbler. Okay. Now this is currently set up well. So from about a magnification of around 100,000 times, we can see the beam here. And with the wobbler turned on, the tilt shifts slightly left and right. And so with the tilt X, which unfortunately you can't see, it's on the other control panel. I'm going to change this to try and minimize the wobble. So you can see now that's reduced. And what that means is that when we do a tilt in the X direction, it's not going to shift the beam by any. So we call that the tilt shift purity because now a change in tilt doesn't introduce a shift. And likewise, we can do it for the Y. So you see now I'm going to correct using the def stig knob Y to correct for that. So you can see if it goes too bad, then the beam starts to split into two. So we get it to the point where there's no splitting and minimize the wobble like so. And now that is set. So now we're ready to do the high tension wobble. So one of the important things to consider when we're doing the high resolution TM is that we want the beam to be passing straight down through the objective lens. If there's any effective beam tilt, that will introduce an effect known as coma, which will degrade the resolution of our image, of our high resolution image. So the on the geo microscopes we have this HT wobble, and this is going to do what's called the voltage centering. On a FEI or thermo microscope, this is called the rotation center, and that does a slightly different alignment, but with the same outcome, having the beam passing straight through the lens. So when I turn on the HT wobble, the first thing we'll notice is that the edges of the beam are expanding and contracting. Now, typically this means that our beam is not parallel-sided, but is focused in. And so I'm going to, with the brightness knob with my left hand, which you can't see, I'm going to spread the beam so that it's barely visible. Okay, and this, just change the automatic contrast brightness. So this now means that our beam is now virtually parallel-sided, and all of our waves are plane waves. And so the wobbler, if there is any beam tilt, if I introduce them, you will see that now with that beam tilt introduced, the image is not only expanding and contracting, but also shifting up and down. And so that's the effect of beam tilt. And we want to untilt the beam. So I'm using the DevStig X, which is currently set up to do the beam align 2 coils, which are the tilt coils on the geo. And you'll see, hopefully, that now when it's set up, the particles are expanding, contracting, rather than shifting left or right or up and down. And we can do the same thing with the X tilt coils. So X tends to go left and right, and we can get it so that the image just expands, contracts, rather than shifting. So now we can be reasonably confident, if I turn the HT wobble off, that our beam is traveling perpendicularly down the objective lens. Okay, so that's the initial alignment complete, and we can now move on to looking at the image. Okay, so I'm going to now shift to using the Catan controls. So for those who aren't familiar with digital micrograph version 3, on the left hand side, this is the program that is used to control the camera. So on the left here we have a schematic of the microscope. We can see we already have the camera inserted, so it's in the column, and it's blue, which means that it's running. currently the screen is down. We can see that here too, which means that the camera is blocked, and so we can't see anything. On the right-hand side, I have control of the camera acquisition and view conditions, and we'll talk about the drift in a short while. Okay, so if I were to raise the screen on the microscope, like so, we can now see the particles. And this leads us to our first topic, if you like, and that is, what magnification do we want to use for high resolution TEM? And it all comes down to resolution. So if we have a look at our image info, we can see the calibration here. So what this number here represents is the effective size of the pixels in the image at this magnification. So we're currently at a magnification of 100,000 times, and our pixel size is 0.12 nanometers. So what that tells us is that any information below 0.12 is not going to be recorded by the camera. So this is effectively our precision. If we increase the magnification then to 200,000, 200,000, and do the same, we can see that our pixel size has reduced by 2, as we would expect. So now this becomes the smallest thing we can see. Now let's have a look. I'm just going to increase the brightness and see if we can see any fringes, any lattice fringes in the image, which we can't just yet. Okay, so on the top right here we have the Fourier transform. So if I just close that, I can show you how we get that. So we go to Process, we go to Live, and I tend to choose Binned FFT, which bins the image by a factor of 2, and then which has the effect of cropping out the center of the Fourier transform. But the Fourier transform here shows us which spatial frequencies are present in our image, and if we keep increasing the magnification, so now we're at 300,000 times. I hope you can see there are 2 spots, maybe one here and one here. And in fact, if I'm quiet, they form a ring around here. So let's just quickly take a 1-second image at this magnification. Okay, so we're not in focus, but that's fine. And if we were to look both at the image and the Fourier transform now, we can see in our image, if we were to zoom in on a particle, that already we're starting to see lattice planes inside the particles. And if we look at the Fourier transform, we can see these rings which correspond with our with those lattice planes, right? So these are the spatial frequencies that correspond to these lattice planes. Now, as a general rule of thumb, we want our planes of interest to lie from the halfway point of the Fourier transform. Okay, so what does that mean? So if we look at these planes here, if we do a line measurement across them, like so, and if we look, just expand it to get a little bit less noise, we can see now there are approximately 5 or 6 pixels between each peak. Okay, this is the minimum number of pixels required to take a measurement. Okay, so on this microscope with this camera at 300,000 times, we can we can see these planes, but if the magnification was very much lower, like 1 or 2 clicks lower, then we would no longer be able to resolve these spatial frequencies. Now, for gold, these are the 111 or the 200 spatial frequencies, which are the very lowest order spatial frequencies that are present, right? So there aren't any lattice fringes that are bigger than these, which means that we need to increase the magnification a bit. So I'm just going to let's go to the full Fourier transform so we can have the same as what I just showed you there. Yeah, it's this. No, that's not live. Process live FFT. So this is what we were just viewing, and you can just see that fringe there. So what we require then is that our highest spatial frequency should be within this circle, right? So this is halfway between the edge and the center. So if I increase the magnification much further, so to 500,000, say, and we can now see even more fringes there and there. And if we now measure the spatial frequency, I'll just change the calibration to be 1 nanometers. No, don't know why this is showing 1 angstrom, but we could equally have per nanometers, yeah. And the resolution of this microscope, so that is the information limit of this microscope, which we didn't discuss yesterday in the theory, but that's the point at which the coherency doesn't let through any more information, is 0.1 nanometers or 10 per nanometers. So 10 per nanometers is 0.1 nanometer resolution, and so at this magnification of 500,000 times, the camera is now recording all of the spatial frequencies present and below what we call the Nyquist sampling frequency. So that's this here, which means that going beyond 500,000 times, we are then oversampling, which means that we'll be reducing the field of view. So we'll be just magnifying on a smaller region, but we won't be increasing the resolution of our images by any, because the resolution is limited by the microscope rather than the camera once we go beyond this 500,000. So if you're using a microscope that's not the F200 with the one view, then I recommend trying to find out what the information limit is, and then what magnification you need to do to get to a situation like this, where your information limit is half of your Fourier transform. Okay, so now we can begin to look at the high resolution images. Now, having said we don't need to go higher than 500,000 times, we're going to be doing the rest of this session at 1 million times, which will hopefully mean that you can see the lattice planes in the image. Okay, so I'm just moving sample around. I'm going to increase the brightness slightly. Let me just do that on the screen. So this brings us on to our our next point. So if we go back to our PDF, and let's go to this table. Okay, so we've talked just there a little bit about magnification. One thing to note is if we go to a high magnification, then things like drift become more of an issue. Because the sample, if it is moving, will move across more pixels, and so the drift will become more obvious. So you can see the sample is moving. What do we do to overcome that movement? Oh, sorry, you can't see the sample moving. So you can now see the sample is moving. So if I move the sample a lot, move it back, then maybe we can say the sample is moving, right? So typically, after moving the sample in the microscope, we want to wait just as a little while to stop any residual movement or any backlash, which is causing this this gradual drift towards the left. In this case, it's towards the left, but it might be in a different direction. Other things that can cause drift are changes in temperature between the microscope and the holder. So if the holder is stored in a separate room that maybe is set to a different temperature, even a few degrees can make a change, and yeah, as that will take around 20 to 40 minutes sometimes for the sample to become in thermal equilibrium with the microscope, with the holder to become in thermal equilibrium, and at that point there's no expansion or contraction of the holder, which is ideal. All right, so going back to our spreadsheet, the next thing to consider is sample thickness. So we mentioned in the theory session yesterday about the weak phase approximation, and while that's more to do with the theory, at thicker samples you get more phase effects, like we saw in the simulated images yesterday, and also perhaps absorption. To get a proper high resolution TM image, a thin sample is best. Now, if I move the controls over here, so we talked about drift. Generally, we need to wait five minutes to settle. Okay, so let's now talk about focus and stigmatism and the effects they will have on our image. So back to our sample. Okay, so here we have a nice particle. Now, maybe the top consideration here I put is a sample tilt. Now, for a nanoparticle-based sample, such as this, we can see that all the nanoparticles that we can observe here have they all have different appearances, right? And that change in appearance is mainly due to the fact that the sample orientation is changing between particles, right? So these were just deposited randomly. Some will grow in the 111 direction. Some will grow in the 100 direction. Because there's an amorphous film, there's not necessarily any particular orientation they will grow in. And you might find that there are defects and things inside them as well. But the long and short of it is that we just have to move the sample around until we find a good one. And in the center here, we have one that is potentially quite good. At least this bottom right area is quite nice, nicely aligned. So I think I hope you can see that. So here we have the dots. So the first thing we're going to do, if I just get back to my binned FFT so it zooms in, what's this? Binned. Okay, so this is now zooming in on that center half. The first thing we're going to do is check the objective stigmatism. In the Fourier transform, there are two things we can see, or three things maybe. There's firstly the center dot, and that corresponds to all of the changes in contrast that you can see here. We then have, so that's really slowly varying, highly varying contrast changes. Around that, we have these rings. So if I change the focus, we can see those rings change. So I'm changing the focus knob here, and we can see how those rings are changing. And I mean, we can also see that they're not round; they are elliptical, and that ellipse changes its long axis from top left to bottom right now to top right to bottom left, and that's an effect of going through focus. So if I turn this now anti-clockwise to get it into that minimum contrast, such as there, then that's where it changes from being top left to bottom right to top right to bottom left. Okay, and that ellipse is caused by objective lens stigmatism. So if we choose the objective lens stigmatism coils, that's going to set the deflector stigmatism knob, the def stig knob, to try and to change the stigmatism values. And like we said yesterday, this stigmatism is focusing the images more strongly in one direction than another. So effectively, we want to make this nice and round. If I go too far, you can see it's now becoming more linear, so that's the wrong direction. If I turn it in one direction, it's now gone more linear in the other direction. So that's quite an extreme change in the objective lens stigmatism, but we want to be somewhere in the middle of those two extremes. And then I'm going to use the X stigmatism coil and do the same thing, okay? And if I do that, we should see this point here where it now becomes round, and that's where the objective stigmatism is corrected, and the image is focusing equally in both directions. Now, yesterday, if we go back to the slides, we looked at the the contrast transfer functions for different foci, and we can see these changes in the transfer function going from positive, which is white atoms on a dark background, to dark atoms on a bright background. If we try to correspond this to the Fourier transform, like here, as we go more and more out of focus, these rings get closer and closer together, and that corresponds with the change of focus here. So going from say more positive in this case, these getting closer and closer to the 0 point here. Okay, so that's what's happening when we change the focus. So how do we get it to minimum contrast in this case? Well, we also said yesterday about focusing using Fresnel fringes. So here, so this is over a hole in the carbon film, but you can likewise use Fresnel fringes at the edges of particles or at the edges of the film. So let's see what that looks like in this example. So here we have the the film out of focus. We can see the rings in the Fourier transform, and we have this bright ring around everything. So what that means is that the sample is under focus, and we need to turn the focus knob clockwise to get to focus. However, if we go too far, we'll start to see that we get a dark ring around everything. And that means that we're now over focused. So we want to go halfway in the middle. And as we get there, what we should see is that the rings in our Fourier transform disappear. And we have no fringe around the particles. Okay, so this is now our minimum contrast condition. Another way of doing this is to look at the carbon film. So if you do have a sample on a carbon film, this is a little bit more challenging to see, perhaps. But when we are slightly out of focus, we can see changes in contrast in the carbon film. Now this is a very thin carbon film, and when we get to minimum contrast, the carbon film should all but disappear. So I hope you can see that there. That is now virtually no contrast from the carbon film, and this gives us our Fourier transform looking like so. Okay. So at this point, we've aligned the microscope, and we've finally focused the carbon film or the sample to minimum contrast. But this isn't the condition we want to use for imaging. We want to use either, we go back, we want to choose some focus value that gives us some kind of sensible result, one that we can then analyze and make sense of in terms of the crystal structure. And like we said yesterday, sometimes at shirts of focus, that's not the best. So shirts focus is the theoretical point where we have this large passband, and the point resolution, so the first crossing of this x-axis, is maximized. But like we said yesterday, if I move my hands, it's not always the case that gives you the most interpretable image, right? So here there are some frequencies that will appear dark on a bright background, but then some which will appear light on a dark background. But if we increase the focus slightly, so in this case to 95 nanometers defocus, then we can get this higher passband where they're all bright on a dark background. All right, so let's see if we can observe that change. Now, whilst I've been talking, the sample has been slowly changing, and that's another thing to consider when doing high resolution TM, is that typically we have high beam currents, or at least a high dose on the sample, which can lead to sample changes in the sample over time. So let's just go to another region that we haven't been looking at. Let's see if we can find another particle that is on the zone axis. Okay, so here looks quite nice. Okay. Sorry. There. So here looks quite nice. I'll move my hands out of the way again. I have this area here in the sample that looks to be near the zone axis. So we're going to adjust our tilt. Adjust our focus so that the carbon film disappears, like so. And you can see now, we were mentioning yesterday the delocalization. There are some fringes extending outside of the nanoparticles. All right. If we look at the dual computer, so that's here. On the right here, it says that we're at 95 nanometers defocus. Now, if I just reset that by changing the magnification up and down, so we didn't make an effective change, let's now set that to 0. Okay, so if we change this now, change the defocus value to minus 65, 63 from that point, we should now be, if we go back to the Catan PC, this should be now our HRTEM condition, okay? And let's just take a quick image. So let's say capture. Okay, and like we said in the slides, in the HRTEM condition, which we should have here, we should have dark atoms on a bright background. Okay, and I think that's what we can see here. Now, this is at the HRTEM condition. If we go back to the dual computer here, and we go down to minus 93, which was our second passband that we showed in the contrast transfer function, and go back to here and take an image, capture. We should now have bright atoms on a dark background. So if we compare these two images side by side, just going to make them the same size. Okay. Yeah. I hope you can now see the effect of focus and the effect that it's had on the contrast, right? So here I'd HRTEM defocus. So that was, I annotate this. This was a minus 65 nanometers. We can see the dark atoms on a bright background, so the atoms appear dark. Whereas here we had at minus 95 nanometers the bright atoms on a dark background, and so that's the effect that we were seeing from the contrast transfer function. The left-hand image was taken in this condition, whereas the right-hand image is taken in this condition. Okay, so I hope that is beginning to make sense. Okay, are there any questions at that point? I've talked for 3/4 of an hour.
Is there any questions? Moment? Any things that you want to ask?
Hi, Richard.
Hello.
Hi, can you go to the first image that you took in the TEM?
Yeah. 2 seconds. This one. Yeah.
Yes.
Hi, Richard.
I'm wondering that the scattering of the particles has some lighter contrast on the sides.
Yeah, these bright bits. Yeah. So that's that is the delocalization that that we mentioned. So for the higher spatial frequencies, they don't get focused to exactly the same point, and that's due to the spherical aberration of the objective lens. So you might notice in your high resolution images that occurs. Now this in this image it's particularly bad, and that's because I hadn't actually focused the image that well. So changing the focus can help a bit. But yeah, that's the delocalization effect.
Understood. Thank you.
Is there any questions? Any other questions?
Hi,
Otherwise,
Richard.
Richard, can I ask you
Hello.
back to the CTF? We can do the simulation to get the CTF. Have you ever tried to measure the CTF from the FFT
Um,
and correlate whether they are about the same?
Yeah. So if you were to do this thoroughly, then what you'd probably want to do is, so I was relying on the value of the microscope outputs, right? So I was saying it shows me that it's 93 nanometers out of focus, and trusting that. If you wanted to do this properly, you should probably calibrate that value, or at least calibrate the step of your focus knob. So how much does each click change the focus by? And you can do that. Probably the easiest way is to do a focus series. So take an image, change the focus, take an image, change the focus, by a set amount, and then yeah, you can you can measure the so in the Fourier transform. I don't know if this one's got it. Yeah, so let's say that one. Yeah, here we have these rings, and if you measure the spacing of each of the rings, I think that gives you a off the top of my head, it's a linear plot, and the intercept is proportional to the spherical aberration, and the slope I think is proportional to the focus. Yeah, and so you can do that for multiple focuses with a set difference between them, and then calibrate how much each click is actually changing the focus by. Yeah.
All right, thank you. I have another question. You mentioned about the number of pixels to measure the lattice spacing. There's about 4 to 5 times. Is there a reason to use 4 to 5 times?
I think that's just the minimum, right? So I think to see the distance between two peaks, right? So you either have if you have say you have 3 pixels between, you'd have one bright, one dark, one bright. Whereas if you have 5, then you have one bright, one in the middle, one dark, one in the middle, one bright. And so I think 5 is the minimum number you need to make that assessment of whether it's just noise or if it is actually a lattice fringe. Yeah.
I see. Thank you very much. Any other questions?
There is one question from the UNSW.
Cool.
Hello.
Hi.
Oh yeah. So at the beginning, Richard Webster, is changing the spot size. Is there any effect on the result or something like that?
So yeah, at the beginning I mentioned changing the spot size and angle. So the spot size is effectively how bright the beam can be, and at lower spot sizes, the uh, the beam is slightly more coherent. So that will give you a little bit more contrast in the image. And yeah, sorry, I've just noticed my battery is on 12%, so I've got a little way to go. The main thing is the angle, right? So changing the angle means that that what you'll call the convergence angle means that you can illuminate a smaller area with a parallel beam, which means that you get a more parallel beam means better contrast. So I think angle 1 is the best for this microscope, and that gives you a better beam condition for the high resolution TM. And it doesn't affect the resolution, but what it does affect is the contrast. Okay, so what that means is that at the higher spatial frequencies, you're going to get slightly more intensity. Yeah. I hope that helps. Maybe I can talk about it after.
Sorry, NTU have one more question.
you.
Give me a minute.
Hi, Richard. Can you demonstrate how tilting the sample will change the zone axis and FFT?
Yes. So I think we have another half an hour left to go. What I'm going to do is quickly change the sample over to a thin film sample. Then I will demonstrate that next.
Okay, thank you.
All right, so I'll change the sample now. Whilst I'm doing that, if you have any questions, I'll be able to answer them shortly. Okay. Okay, so we're just waiting for the holder to insert. While we do that, there are two things really that are different for thin film samples. One is the sample tilt, like you mentioned, and I'll demonstrate how to correct that. The other thing is generally the lack of amorphous region. So when the sample is suspended on a carbon film or a silicon nitride grid, that background is amorphous, and that gives you those rings very readily. Whereas with a fib sample, it's quite uncommon to have that amorphous material present. Now, there's two things, two ways you can get around it. The first is you sometimes have the platinum region on the top. So when you make the fib sample, you deposit platinum in the fib, and that's not a continuous film of platinum. It's quite discrete, and in between, it's filled with amorphous carbon or amorphous carbon and platinum. So that can be used for the alignment. Failing that, you might have a glue line from a mechanically polished sample, or on a fib sample at the very base, it's possible that there could be redeposited material from the fib, so damaged material, and that might be amorphous. Generally speaking, there will be some region of amorphous material you can use for the alignment. It just might not be ideal. So just bear that in mind. So if we go back to the, sorry, did anyone have any questions before I begin this second part? So let's. So this is a fib sample. I don't know if you're all familiar with fib samples, but they're slightly different to your regular TM sample in that they're on a different shaped stub. Okay, so that's promising. So what we're following is the grid along, and then we should see in a short while the sample sticking out the side, I hope. I think this might not have worked. So in Lomag, yeah. The sample should be here, but it disappeared. So I'm going to quickly change the sample again. Try this again. All right, second time lucky. All right, so this is the dual computer. Here we have the fib sample sticking out of the end of the TM grid. The half moon grid used for the sample prep. And what's it again? Here we are. Okay, so you can see here we have this this transparent area. Yeah, so you can see we have this long, thin, transparent area, and we have this the dark bit at the top. That is the platinum film I was talking about using that we can use before. So if we just start and try and do some high resolution TM straight away, now our alignment should be fairly good from the previous sample, and apart from some damage. So this is a strontium titanate, which is just a single film. We're going to use make sure it's standard focus. I'm going to use the Z to get rid of this Fresnel fringe. So that's moving the sample up. So it disappears. That's minimum contrast. Let's go to 1 million times and go to the Gatan PC. It's here. And insert the camera again. And lift the screen. Okay. It's still a little bit out of focus. So let's just adjust that. So no Fresnel fringe. Okay, so this is what the what the image looks like. Now you can see I've just put the sample holder in, and I hope you can see that the sample is drifting towards the left again here. So that's probably that change in temperature. So this holder is kept in the same room, but there's still going to be a slight change in temperature between the cooled objective lens and the microscope and the holder. But you can see that in the Fourier transform, the main difference between the gold particle sample and this single film of strontium titanate is that instead of the rings we were getting for the gold particles of different orientation, we have these solid peaks, which are due to the crystallinity of the single crystal nature of the SGO. However, so this is near. Let's go like say somewhere like here. This is near HRTEM focus condition, but we're not getting anywhere near the contrast we might expect with kind of cubic symmetry in our high resolution image. So if I just try and capture an image quickly, doesn't work too well. It's not great. So the reason for that is that the sample isn't tilted towards the zone axis. So if we put the screen down and go back to the jail computer. Let's see. Just do something here. Is that better? Sorry, just having an issue with the mouse there. Yeah, so we want to orientate the sample. Okay, so I'm just going to decrease the magnification slightly. Center the beam. Okay, so we're going to use convergent beam diffraction to try and orientate the sample. So if we converge the beam using the brightness knob, which is on the left-hand side, and we can go to diffraction now, and then if I just change this to be linear scale, that might make it easier to see. In the current condition, you can see that our sample zone axis is down in the bottom right down here, whereas our direct beam is here. And what that means is that there's only one set of planes that are really parallel with the beam and are strongly diffracting. Now, for high resolution TM images, what that means is that instead of getting a cross-grading pattern, we get just a single set of fringes that are strongly diffracting and strongly contributing to our image. So in this case, it's this plane. I don't know if you can see that very well, but you can see the plane from top left to bottom right is the most strongly diffracting, and that corresponds in the diffraction pattern. So if I switch to this plane here. So what we want to do, if I just increase the exposure a little bit to make it see easier, is we want the zone axis. So that's where these Kikuchi lines intersect down here, to move up here. And the way we do that is by tilting the sample. So on the sample controller, the goniometer controller, we have the tilt controls, which are these four here. So we have X, which are on the left and right hand side, and we have the Y, which are up and down. Now, between the image and the controller, there's a 90-degree rotation. So what that means is if I rotate the controller around by 90 degrees anti-clockwise, the positive tilt direction, if I am able to annotate this, this is the positive tilt X direction. Oops. And likewise, this is the positive tilt Y direction. Okay, and what that means is if I want to get the zone axis from down here to up here, first I need to tilt in the X direction, positive. So if I do that, we can see, so I'm now pressing the button down, we can see that the zone axis is moving closer and closer and closer towards the transmitter disk. Now, there's been some sample movement. So if we go back to magnification and spread the beam, we can see now that our sample has moved away from where the beam was. So I need to move the sample back with the X controller, sorry, the trackball, and now we can try again. So back to diffraction, and likewise linear. So now you can see here is our zone axis, and we still have a little way to go. So roughly 5 degrees maybe. don't know. If I keep going, you can see that these are getting closer and closer. Now, if I reduce the exposure time, it might make it easier. So now you can see we're not quite on the zone axis. I might just increase here. So this is our transmitted beam, but we're slightly towards the right-hand side. There's a little bit of asymmetry. So that means I need to do a small amount, and I mean small, maybe half a degree of Y tilt. So if I do that, like so, we should get to a point where I'm doing some sample movement as well to get it back as it adjusts. But what we should see now is that we have this perfectly symmetrical diffraction pattern. Now, it might not be exactly symmetric, but it'll be good enough for the purpose of this demo. I think something like that. Looks very symmetric to me. So if we now look at the Kikuchi lines, just by decreasing the camera length, we can see that they are now all passing through the center of our diffraction pattern. And that indicates that we're now on the zone axis. And so going back to magnification mode, we can spread the beam and move back to the edge. Going to 1 million, like we had before. Okay. And we can now, let's go back to the Jill, the Gatan camera. So it'll be this one. And viewing it here. All right, so hopefully we can see a difference straight away. Now we haven't done any focusing or anything like that, but if I take the image, so, and then go back to the and compare the two images, we can now see on the image that is orientated to the zone axis, we get a much more well, our image now has the symmetry of the lattice rather than before, where we had just the single planes. So orientating the image, orientating the sample to the zone axis means that we get more planes contributing to the interference pattern that is our high resolution image. So there's yeah. So this gives us a better view of our sample. And if we look at the Fourier transform, which tells us about those spatial frequencies, we can see in the latter case, because we're on the zone axis, there's a lot more planes contributing to the image, and so we have more spots, which means higher resolution. Okay, so yeah, so let's try and take a nice image. So we're going to go to standard focus, like so. So that's the standard focus value, and then we're going to use the Z controller. So I'm going to use the Z up in this case, just to make sure that we're at the right height. Okay, and then now we were mentioning before about the amorphous material. Now we can see we still have some rings inside of our Fourier transform. The presence of those rings means that there is some amorphous material, and we can see at the edge here we have either a damaged layer from the fib or maybe the sample has contaminated, producing some amorphous contamination. But in either case, we can use that for our objective lens stigmatism. So we can see that it's not very round at the moment. So if I choose the objective stigmatism coils, we can again go and correct that. So making this nice and circular. Like so. One thing that can be handy is to draw a circle on our Fourier transform. So if we hold down Control and Shift and drag from the center, we can just make sure it is in the center. We can try and get that as close as we can. Yeah. Okay, so that's pretty good. And then we can use the focus knob for our fine focus adjustment. So I'm looking now. Okay, so the other difference a big difference that we have between thin films and particles suspended on a film of carbon is how we focus, right? So with a thin film like this, we tend to have an edge that we can use for our focusing. So we can see if we go too far anti-clockwise with the focus knob, we get a bright Fresnel fringe. And again, if we go towards the right too far clockwise, then we get a dark line. And in effect, we want to be where there's no line. So if again, we're just going to get to the minimum contrast condition, which is around there. But that is now minimum contrast where there is no Fresnel fringe, and we can see what that looks like in the FFT. Wow, that's quite nice. Okay. So there's one thing we can see, and that's the flicker in the spatial frequency in the Fourier transform. And what you might notice is that that only occurs when I'm talking, and the reason for that is that, well, there are two reasons. One is I'm talking. The sound waves or the air pressure variations are hitting the end of the specimen rod, and it's acting like a microphone. So I think you can see behind me here that I don't have the screen cover closed that I normally would, and that's because I'm using it to suspend the camera so you can see down here. So one way to reduce this effect would be to close the goniometer case. Sorry, I misspoke before, the goniometer case. If that's closed, then that protects the holder from vibrations such as noise. Yeah, and of course the other way to prevent this is when you're taking your images, not to talk, to be quiet and still, and try to minimize any vibrations in the room. So if you have a friend with you on the microscope and they're talking a lot, maybe just tell them to be quiet whilst you're taking the images, and that will just help with the quality. So yeah, let's go back to focus. So this is a minimum contrast. I don't think there might not be too much difference now between the Schürze and the minimum contrast, but we'll see how this looks. So I'm going to go back to looking at the geo screen here, and we're going to go to minus 65 like we had before. Yeah. And like I pointed out, there could be some inaccuracy with this value, but we're going to trust it for now. And let's take the image. Oops. And now I'm going to go to 95, minus 95, sorry. And let's just compare those two images. Yeah. So I think around here we can start to see some variations which might be consistent with with the lattice image, with the variations that we'd expect from the lattice. But the majority of the variations we can see across from the left-hand side to the right-hand side are probably due to the thickness effects that we mentioned in the talk yesterday. As the thickness increases, then we see changes in the contrast in the high resolution image. And so, yeah, I think that's what we can see going from left to right. So, I don't know. In the center here, you can see it's very complex. It's not necessarily going to give you a good lattice image, and that's probably a poor. Yeah, just a bad thickness for this particular sample. But then somewhere down here, it is giving you the correct symmetry. Yeah. Okay. So, are there any questions about the thin film high resolution TM?
NTU students, any questions about?
There is one question from UNSW.
Oh, yeah.
Sorry, Charlie. Is it the atom in white color?
Good question. I think we wouldn't be able to answer that question without careful comparison to simulations. You can see on the left-hand side here that we have these kind of dumbbell effects. And I suspect that in this area, due to the thickness, the atoms are dark. But maybe on the right-hand side here, you can see there's a change, this transition period, and then here, maybe they're bright. But again, we would need to do something similar to what we had in the slides yesterday, where we either do something like this, a thickness focus tableau, so we have focus along the bottom, thickness along the top, and then we can see that change in contrast as a result of changing focus or changing thickness going up there. Yeah, and so without comparing to the simulation, it's difficult to say which one is dark, like if the atoms are bright or dark. Yeah, because it is so intimately linked to the imaging conditions, thickness and focus. Yeah, good question,
Richard?
though. Yep.
Richard, can I ask you, for the image that you have just taken, is it still reasonable to use the GPA analysis on that image?
On this image, yes, I would say so. Now here you're not going to see much difference. I wouldn't think, because it is just a thin film. I mean, ideally, your sample would all be the same thickness and all the same orientation for GPA analysis. But I think you would still get something reasonable, I think, out of an image like this. Yeah.
Sure, thank you. Is there any other questions for NTU? Just hold.
Yeah, thanks for the nice talk. Yeah, can I know the sample you just mentioned the prepared by FIB? How about the FIB process? Do you know use the low kV 2 kV or even 1 kV to low polish?
Yeah. So this sample was prepared on our plasma FIB. So we have a Thermo Fisher xenon plasma FIB, and this sample was using 30 kV for the initial polishing, and then finally with a rectangle polish at 5 kV, and then at UNSW we have the Fishioni nanomill, which is an argon ion beam item, like instrument, and that it's so similar to pips, but has a much finer beam. And what that can do is we can remove the surface of the sample, so that the surface, which can be the part where you have contamination, or the part which has the damage layers, and so you see the damage layer here is maybe 2 nanometers thick. Yeah, and that was attempted to be removed with the nanomill, with the argon ion nanomill. Yeah.
Thank you.
Well, no problem. This is quite an old sample, so it might have oxidized or contaminated over the course of the last year or so.
Yeah. Nice.
Any more questions from NTU?
There is one question from the UNSW.
Yep.
Hello, Richard. I'm just wondering what's the camera lens you're using when you're adjusting the Gucci lines?
I used 1200, but that was mainly just so that you could see it on the screen. Yeah, normally I think I use around 600 or 800, just so I can see it on the fluorescent screen. Yeah.
Thank you.
There is one question again from UNSW.
Yeah.
Yesterday you mentioned about we need to really care about the analyzing the HRTM, like for example, in the case of we have some overlapping lattice, like 9R case. Is there any like technique or is there any technique like kind of to resolve this one, like maybe changing the angle of the beam or tilt the sample, or
Yeah, good question. So it can be useful to image the sample in 2 different orientations. So so here we're orientated to the 100 orientation. That's going to give you some information about the lattice from that orientation. Tilting to another orientation, such as the 110, so that's going to be 45 degrees of tilt, which is going to be challenging depending on which pole piece you have. But certainly, looking at the sample in different orientations is going to help. It might mean that you need to make 2 samples, one for 100 and one for 110, of slightly different areas. But yeah, it's definitely going to help if you've got a challenging sample like that one. I think looking at different orientations is best, but it's not always practical. I think that's the point. But certainly doing other techniques, right? So high resolution TM doesn't stand on its own. I think you should do diffraction of the same area. If not, just to record the conditions that you took the high resolution TM at, but also to record the for the crystallinity of the sample. Yeah, and yeah, comparing the simulation helps as well.
Thank you.
Hope that helped.
Well, I guess there's no more question from NTU side. So thank you very much, Richard, for the demonstration.
Well, thank you for your attention. And I think on Thursday, YY will be giving the talk on
We'll be giving the
on
talk on
diffraction.
the electron diffraction.
Yeah. All right. So we look forward to
And-
that.
Yeah,
And,
sure.
All right. See you on Thursday.
Yep. See you guys. See you. Bye bye. Thank you.
Bye.